Hello everyone, I'm Dr. Amit. Welcome back to our pharmacology series. If you are preparing for your MBBS professional exam, USMLE Step 1 or any PG entrance, today's topic is an absolute must know. So we are diving into Line-Weaver-Burk plot, okay? So today's topic is Line-Weaver-Burk plot. So this is the plotting figure, okay? So the double reciprocal plot that makes enzyme kinetics actually readable, okay? So before we jump into the maths and the graphs, make sure to hit that subscribe button and turn on notifications so you don't miss any of our high-yield medical breakdowns, okay? So are you ready? So let's get started our topic. So first let's understand what is this Line-Weaver-Burk plot, okay? So in basic biochemistry we actually look at velocity versus substrate concentration, which gives us a hyperbolic curve, okay, as we have already discussed it in the previous video, Michaelis-Menten kinetics, okay. But let's be honest, curves are hard to calculate, yeah. So to simplify that things, we use this Line-Weaver-Burk plot, okay. So instead of plotting V versus S, okay, we plot reciprocals, that is 1 by V versus 1 by S, okay. So and it's give a straight line. We are using the formula y equal to mx plus c, okay, the equations of a straight line, okay. So we can say that it is a straight line graph used to simplify enzyme kinetics. We don't plot velocity versus substrate in this, okay. We plot 1 upon v versus 1 upon s, which gives us a straight line, okay. So let's how to read this graph, okay. So we all know this is y-axis and this is x-axis, okay. So y-axis denote 1 by v and the x-axis denote 1 by s, okay. Now the slope will be km by vmax, and the y-intercept, okay, the intercept over here on the y-axis, it denotes 1 by vmax, and the x-intercept over here, this is 1 by km, okay. So why the scientists develop this, or the doctors develop Line-Weaver-Burk plot, okay. So because the straight lines are easier to analyze and it helps us to calculate km and vmax easily, okay, and identify the type of inhibitions, okay. Now we'll talk about different inhibition. Now we'll link this Line-Weaver-Burk plot with the inhibitors, okay. So we all know there are three types, okay, as from the previous video: competitive inhibition, non-competitive, and on-competitive inhibition, okay. So while talking about competitive inhibitions, okay, the Vmax will remain same and Km will increase, okay. So you can also remember that competitive, okay, KOM, okay, we can write this as competitive. So K will increase K, okay. So on the graph, okay, we all know the line meets at y-axis, okay. So now let's understand with this figure, okay. Suppose this is the enzyme and these are the active sites of the enzyme, okay, and these are the substrate and these are the competitive inhibitors, okay. So if this substrate wants to come in this home, okay, in this home, then this competitive inhibitor will block, will try to sit in this room, okay. So they will compete with each other to stay in this room. In the same way, if this come over here, then this will inhibit this, okay. This will try to compete with this, okay. The same thing will happen in the rest of the rooms, okay. So that's why, but the room is fixed, okay. So the Vmax will not change, but more and more substrate we need to push these inhibitors out, okay. So that's why the Km increases, okay. The substrate to reach half of Vmax will increase, okay. And we all know from this graph, okay. So over here, okay, this denotes the y intercepting over the y-axis. This is a half of Vmax, okay. So this also denote the competitive inhibitors, okay. Now we'll talk about non-competitive inhibitors, okay. So in these conditions, the Vmax will decrease and Km will remain same, okay. So in non-competitive, no change in Km, okay. And this line meet at x-axis, okay. So wherever the line will meet on x-axis, that will be the denote a non-competitive inhibitors, okay. So over here, if you will see that, if suppose these are the non-competitors, so okay, these are the non-competitors, so it will not compete with this, okay. It will not compete with this, but what they will do, they will sit somewhere else, okay, and that will decrease the enzyme activity, and that's lead to decrease in Vmax. Suppose these are the non-competitors, okay, it will sit over here, but this will decrease enzyme activity, okay, and that's why the Vmax will decrease, the Km will remain same, okay. In the same way, if you'll see in the uncompetitive inhibitors, the Vmax and Km both will change, because the uncompetitive inhibitors will bind with this complex, okay, and decrease both Vmax and Km, okay. So if on graph you will see the lines are parallel, okay, the parallel lines will denotes the uncompetitive inhibitors, okay. So whenever if you get any MCQs, okay, and you'll get the lines, okay, so the line where it intercept on the y-axis, that will denote the competitive, where it will intercept on the x-axis, that will denote the non-competitive, and if it will come parallel, then that will be uncompetitive inhibitors, okay. So this wraps off our breakdown of the line weaver-Burk plot. If you can visualize where those line meets, okay, you'll never get these questions wrong again, okay. So thank you so much for watching. In our next video, we'll be talking more on pharmacology, okay. So stay tuned. If you found this video helpful, please subscribe and give us a thumbs up and share this video with your study group. Happy studying. I'll see you in the next one. Thank you.